For most of human history, the physical world appeared to operate with no discernible rules. You could burn wood, watch it turn to smoke and ash, and have no way to explain the chemical reality of what occurred. The Greek philosopher Aristotle offered an answer. All matter was a combination of 4 basic elements: earth, water, air, and fire. While this was scientifically inaccurate, it remained the dominant explanation for nearly 2,000 years. Without a correct definition of what an element actually was, chemical progress stalled. By the Middle Ages, alchemists isolated new substances like mercury and sulfur. However, they worked through trial and error. Their discoveries lacked any unifying organization. Identifying individual substances was a start, but it wasn't enough. Chemistry could only become a science once it had a framework to explain how all matter relates. In 1789, Antoine Lavoisier discarded ancient myths to establish a new foundation. He is called the father of modern chemistry for his rigorous, evidence-based approach. Lavoisier introduced a strict definition. An element is a substance that cannot be broken down into anything simpler by chemical means. He identified 33 elements and sorted them into broad categories, such as metals, nonmetals, and gases. This was progress, but it was incomplete. Sorting elements by their state of matter is helpful for inventory, but it fails to explain the complex ways these different substances interact with one another. In 1817, Johann Döbereiner noticed a mathematical pattern. He found sets of 3 elements, like lithium, sodium, and potassium, where the mass of the middle element perfectly averaged the other 2. John Newlands built on this in 1864 with his law of octaves. He observed that when elements were arranged by mass, every 8th element showed identical chemical behaviors, repeating like a musical scale. But the pattern was fragile. As heavier elements were discovered and added to the list, Newlands' rows of 8 began to misalign, and the system fell apart. These repeating patterns suggested that the elements followed a predictable rhythm. The problem was that atomic mass, the weight of the atom, wasn't the correct metric to explain it. In 1869, Dmitri Mendeleev solved the puzzle by prioritizing chemical properties over a rigid numerical list. He built a grid where elements were sorted by mass, but he left skipped spaces intentionally blank whenever the chemical properties didn't align. He insisted that these gaps represented matter that simply hadn't been discovered yet. This made the table a predictive engine. By looking at the elements surrounding a gap, Mendeleev was able to accurately forecast the traits of undiscovered elements like gallium and germanium. However, Mendeleev had to break his own rules to make the table work. In certain spots, he was forced to place a heavier element before a lighter one, swapping their positions to keep their chemical properties in the correct column. Mendeleev had found the correct layout for the elements, but the numbering system he used to order them was still out of sync with reality. In 1913, Henry Moseley used X-ray experiments to find the missing link. Moseley discovered that the true identity of an element isn't its mass, but its atomic number, the exact count of protons in its nucleus. Sorting the periodic table by proton count instead of weight solved every lingering inconsistency. The elements that Mendeleev had to swap now snap into a perfect unbroken sequence. Moseley's discovery of the atomic number provided the definitive physical proof of how the elements are built. The modern table was later refined by scientists like Glenn T. Seaborg, who used quantum mechanics to integrate the heaviest elements into the actinide series at the bottom of the chart. What began as a philosophical guess of earth and fire has evolved into a precise catalog of 118 confirmed elements. This table is an active tool for the future. It is the essential guide used for engineering new materials, monitoring our environment, and developing modern medicine. Through a 2,000-year relay race of discovery, humanity transformed a chaotic world into an elegant and masterable blueprint.